Welcome to the deep dive. Today, we're plunging into a stack of sources that, well, they tackle one of the really pressing challenges facing AI right now. How do we take these incredibly powerful, insightful language models we've built and, make them smart and capable enough to actually run on devices that don't have massive data centers backing them up? Think about it, your phone, maybe a smart speaker, even the AI system potentially in your car.
It's a fundamental hurdle, isn't it? The
Mm.
sheer size and, frankly, the computational demands of these large language models, they just clash directly with the really strict memory and processing limits you find on smaller edge devices. You can't just, cram GPT-4 onto a chip designed for your toaster. Well, not yet anyway.
Mm.
And while the big models get all the headlines, they're notorious memory hogs, especially when it comes to their ability to keep track of the conversation history or the text history, what's technically known as the KV cache.
Yes, the KV cache. The sources we're looking at today really zero in on this as a major bottleneck. In standard transformer models, like the ones underpinning most LLMs, generating text token by token requires storing these key and value representations for the entire sequence seen so far, right in this cache.
And the problem is, the memory you need for this KV cache, it scales linearly with the sequence length.
Linearly, so longer text means proportionally more memory.
Exactly. The sources give us the formula. It's roughly proportional to the sequence length, let's call it n, times the number of attention heads, h times the dimension per head, DQO. So if you want longer conversations or you need to analyze longer documents, that cache size just explodes. It becomes prohibitive very quickly.
And that linear scaling is precisely what can cripple deployment on, well, memory-constrained hardware.
Definitely. But at the same time, it's interesting, work on models like tiny stories has shown that even really small models, maybe under 10 million parameters, can exhibit surprisingly sophisticated linguistic abilities for specific tasks.
It's not just about being massive.
It suggests not. It implies that architectural efficiency, especially in managing things like the KV cache, is absolutely critical for making AI practical and, ubiquitous, not just raw size.
Okay, so our mission for this deep dive then is to unpack a recent research paper, one that directly addresses this KV cache problem. It proposes a really clever solution using two specific techniques: latent multi-head attention, or MLA, and rotary positional embeddings, RoPE. We're going to focus particularly on the academic insights they uncover and the innovative ways they approach this efficiency challenge. Let's unpack this.
All right, so the first core innovation the paper presents is this latent multi-head attention, MLA. The fundamental idea is quite elegant, actually. Find a way to compress those key K and value V representations before they even get stored in the KV cache.
Compress them. How do they manage to squeeze that information down effectively? Sounds a bit like you might lose something important.
Well, that's the trick, right? It's about learning what's important. MLA introduces what they call a bottleneck into the process of calculating K and V. Instead of calculating the final K and V directly from the input in one step, they factorize that projection.
Factorize, meaning break it down.
Exactly. For each attention head, the input goes through two smaller linear transformations. First, it's projected down into a smaller intermediate representation. They call this a latent representation. Then that smaller latent representation is projected back up to the final K or V size needed for the attention calculation itself.
So it's two steps down, then back up instead of one direct step.
Precisely. But here's the really clever part for efficiency, especially during inference, when the model's actually generating text. You don't cache the final full-size K and V for the whole sequence history. You only cache those intermediate compressed latent representations.
Ah, I see, because those are smaller.
Exactly. Since that latent dimension, they call it R, is specifically chosen to be smaller than the original per head dimension, dk, the memory needed for the cache drops. It goes from being proportional to NHTKO down to 92 error.
Got it. Because R is smaller than DK, you save memory. Simple as that.
Well, the concept is simple, but the execution is learned. And if we're the same size as DK, there'd be no compression, and MLA would essentially just behave like standard multi-head attention, MHA.
Okay. And you said this factorization, this down then up projection, it's learned.
Yes, that's crucial. The model learns during training how to best perform this compression and decompression. It's essentially learning a low-rank projection mechanism designed to identify and preserve the most critical information for the attention mechanism, even within that compressed form.
Okay, so MLA handles compressing the K and V states to save cache memory. But language models also need to understand the order of words, right? Their position in the sequence. How does that fit into this MLA picture?
Great question. That brings us to the second piece, positional embeddings. Standard MHA might just add explicit embeddings based on position. But this paper specifically investigates using rotary positional embeddings, or RoPE, alongside MLA.
RoPE. Right, that encodes position using rotations somehow. I know it's often cited for helping models handle longer sequences better.
Yes, that's its key strength. RoPE applies rotation matrices to the query and key vectors. The angle of rotation depends on the token's position in the sequence. This effectively encodes relative positional information, which is particularly good for generalizing or extrapolating to sequence lengths the model didn't even see during training. But the real academic question this study digs into is the interaction. How does RoPE behave when combined with MLA's compressed attention? Do they play nicely together?
And what did they find? What's the headline result when they combine MLA and RoPE?
The primary finding, and this is really the core claim, is that this combination offers what they term a Pareto improvement for small language models.
Pareto improvement, meaning you gain on one front without losing much on another.
Exactly. In this context, it means you achieve significant gains in efficiency, memory saving, speed, without incurring meaningful losses in the model's quality or performance.
Getting more efficient without making the model noticeably dumber? That sounds ideal.
It really is. And the numbers they present are quite striking. By combining MLA with RoPE and using what they call a half-rank latent dimension, so setting R to be half of D key, they achieved a really substantial 45% reduction in KV cache memory.
Wow, 45% less memory. For anyone building AI for devices with limited RAM, that's huge.
It's enormous. And it wasn't just memory.
What about speed? Did compressing the cache also speed things up?
Yes, it did. Especially when you look at scenarios with larger batch sizes, which are common in server-side deployments or high-throughput situations. They observed a 1.4x inference speedup compared to using MLA plus RoPE, but with the full latent dimension, so where R equals D.
So less memory and faster generation, that seems like the holy grail. But what about that quality hit? They mentioned a 0.3% increase in validation loss. Is that truly negligible?
That's a fair point. 0.3% increase in validation loss is small. It suggests the model is only slightly less accurate at predicting the very next token compared to the standard vanilla MHA. For many applications, you'd probably say that's an entirely acceptable trade-off for getting nearly half the memory usage and a 40% speed boost.
But maybe not for everything?
Perhaps not. If you have extremely sensitive tasks, maybe critical control systems or certain kinds of medical text generation, even tiny errors might be problematic. You need to weigh that trade-off carefully. But the paper's main finding is that for small models on general tasks, like the story generation they tested, this level of quality preservation is achievable alongside those big efficiency wins.
Fascinating. It really does sound like this MLA plus RoPE combination is a potent one. But let's dig a bit deeper into why RoPE is apparently so crucial here. What happens if you just use MLA without RoPE?
This is where the academic insight gets really interesting and maybe a bit surprising. The sources show that if you implement MLA, even at full rank, so R equals D, meaning no actual compression is happening yet, but you do it without any positional encoding like RoPE, it actually performs worse than standard MHA.
Worse, even without compression.
Yes. They reported something like a 3–5% increase in validation loss compared to standard MHA.
Wait, so just the act of adding that factorization step, that down and up projection, makes small models a bit worse if they don't have clear positional information. Why would that be?
It seems. Well, the hypothesis is that the extra computational steps, or maybe just the slightly different data flow introduced by the factorization, can slightly disrupt the model's ability to learn effectively, particularly in these smaller models. Unless you provide strong positional context, it's like you've added a slight detour in how the information flows. And without a clear map, the positional EFO from RoPE, the model gets a bit lost navigating that detour.
Okay, that makes sense. But then what happens when you add RoPE back in?
This is the kicker. When you add RoPE back in, MLA plus RoPE, at full rank, RD, doesn't just recover that performance loss compared to vanilla MHA. It actually surpasses vanilla MHA.
Surpasses it by how much?
By about 2% lower validation loss, according to their results.
Wow. So RoPE doesn't just fix the problem MLA might introduce on its own. It actually makes MLA better than the standard approach, even before you start compressing. That's quite counterintuitive.
It is. It suggests a strong synergy.
Why does RoPE have this almost like protective or even enhancing effect, specifically with MLA?
The researchers suggest RoPE provides crucial structural information. By encoding relative positions through these rotations, RoPE seems to give the model a much stronger inherent sense of sequence structure. This structural awareness appears to compensate for any potential information loss or disruption caused by the MLA factorization, and later, the compression. It helps the model maintain things like narrative consistency and relationships between words, even when the core attention mechanism itself is being made more efficient through compression. This protective effect, as they sometimes call it, becomes particularly vital when you start really cranking down that latent dimension R and compressing more aggressively.
Okay, so RoPE provides the structural map that lets MLA's compression shortcuts still lead to the right place, maybe even a better place than the original row. That clarifies things. And you mentioned R, the latent dimension, is the knob that controls the trade-off. How does changing R specifically impact memory, speed, and quality? Let's break that down.
Right. Memory savings are the most straightforward part. As the sources clearly show in their graphs, the KV cache memory usage scales pretty much linearly with R. Reduce R by half, you cut cache memory roughly in half. Reduce R to D8 like they tested, you get roughly an 8x reduction in cache size compared to using the full dimension. Super direct.
Okay, clear linear trade-off for memory. Makes sense. What about speed? Is it also a simple linear relationship?
Speed is more nuanced. Inference speedup turns out to be more complex, and it depends quite a bit on how you're running the model specifically, the batch size you're using.
Batch size, how many sequences you process at once?
Exactly. The sources provide a really insightful graph showing throughput, like tokens generated per second versus batch size. For standard MHA, the throughput actually tends to decrease at larger batch sizes.
Wait, MHA gets slower per sequence when you give it more work to do in parallel. Why?
Yeah, it seems odd at first. It's because processing those large K and V matrices in standard MHA requires significant memory bandwidth. At larger batch sizes, the computation becomes bottlenecked by how fast you can shuttle data between the processor and the main memory. It becomes memory bound.
Okay, limited by the data pipeline.
Right. Now, here's the fascinating academic detail about hardware interaction revealed by the study. The MLA variants behave differently. Their throughput actually tends to improve as the batch size grows, at least up to a certain point.
That's completely the opposite. Why would making the batch size bigger help MLA run faster per sequence?
It's because the core attention calculation in MLA happens on those much smaller times R latent matrices, not the full Aperi times DKOR matrices used in MHA's main calculation. This smaller computation is far more likely to fit entirely within the processor's really fast on-chip memory, the SRAM or L2 cache, especially at larger batch sizes where you're doing many computations. This leads to significantly better cache locality, less time wasted fetching data from slower main memory. It boosts throughput dramatically.
So by making the central calculation smaller with MLA, it can leverage the fast on-chip memory much more effectively when processing multiple sequences simultaneously. That's really clever hardware-software interaction.
It's a great example of how algorithmic changes can unlock hardware potential. And the numbers they show bear this out. MLA with RD4, which is pretty compressed, starts a bit slower than MHA at tiny batch sizes, but it actually overtakes MHA's throughput by 9% once you reach a batch size of 32. And MLA with RDD2, which gave that 45% memory saving, also performs really well on speed, only about 4% behind the RD4 variant at batch 32. So you get fantastic memory savings and strong speed, especially in parallel processing scenarios.
And does RoPE affect the speed much?
Adding RoPE does slightly increase the raw number of calculations, the arithmetic intensity. They note it reduces throughput by a small amount, maybe around 15 tokens per second in their setup. But fundamentally, the speed benefits coming from MLA's memory compression and the quality or robustness benefits coming from RoPE seem to be largely independent or orthogonal.
Okay, so you get speed from MLA's cache efficiency and quality and robustness from RoPE. Makes sense. But going back to R, the compression level, there must be a point where you compress too much and quality just, falls off a cliff, right?
Absolutely. You can't compress indefinitely. And the study observes what they describe as a critical phase transition. This seems to occur somewhere around RE16 in their experiments, so compressing the latent dimension down to 1/16th of the original head dimension.
A critical phase transition sounds dramatic. What happens?
Beyond this compression level, the validation loss, the measure of prediction error, starts increasing exponentially, not linearly, but shooting up very rapidly.
Exponentially. So things fall apart very, very quickly past that point.
They really do. At the most extreme compression they tested, which is RD32, the validation loss increased by over 20%, and the model effectively became unusable. The sources note that models compressed this much essentially just generate random token sequences. Complete gibberish, no coherence at all.
Wow. Random tokens. That really drives home the point that there's a hard limit.
And an interesting academic finding they mention is that this catastrophic degradation seems to be more abrupt in these small, tiny stories models compared to observations in some much larger models where similar compression techniques have been tried.
So smaller models might be less forgiving of extreme compression.
That seems to be the implication, yeah. Less capacity to compensate.
Okay, so validation loss tells us when things go completely off the rails. But how did they measure the quality of the generated text in that middle ground? Beyond just that abstract number, did they look at the output?
Yes, and that's another quite novel aspect of their methodology, especially for evaluating smaller models.
Yeah.
Beyond the standard perplexity or validation loss, which basically just measures how well the model predicts the next token, they performed automated qualitative evaluation using GPT-4.
Using GPT-4 to evaluate other models, that's pretty meta. How did that work? What did they ask GPT-4 to look for?
They developed a structured rubric. They had GPT-4 score 100 different story completions generated by each of the model variants they tested. The rubric focused on 3 specific aspects: grammar, creativity, and crucially, narrative consistency.
Grammar, creativity, consistency. Okay. Did the GPT-4 scores line up with the validation loss results?
Yes, they said the GPT-4 scores strongly corroborated the perplexity findings. The MLA+RoPE model with RD2, the one with good efficiency and low loss increase, also received the highest overall score from GPT-4, 7.4 out of 10. And interestingly, it particularly stood out in the consistency and creativity scores compared to standard MHA or MLA without RoPE. So the automated scores gave a more granular insight into what was better.
Which of those scores, grammar, creativity, consistency, seemed most sensitive to the compression? Where did things break down first, according to GPT-4?
Consistency. They identified consistency as a kind of canary metric. It showed the steepest drop as the compression ratio increased or got smaller.
The canary in the coal mine.
Exactly. It suggested that reducing the attention capacity via compression primarily impacts the model's ability to track the narrative state, remember what happened earlier, and maintain coherence over longer sequences.
So when compression gets too high, the story starts falling apart first, losing the plot. Makes sense. Looking at the actual generated stories must provide the most vivid examples of these differences. What did the outputs actually look like?
Yeah, they provide some great qualitative examples in the paper that really illustrate these academic findings. For instance, MLA without RoPE often produced narratives described as incoherent or repetitive. You'd see disjointed plot shifts, awkward phrasing, or characters doing things that didn't make sense based on earlier parts of the story, directly reflecting those poor consistency scores.
Like it was trying to tell a story but kept forgetting the beginning or getting lost?
Exactly. Then you have the vanilla MHA outputs. These were generally grammatically fine, and the characters usually stayed consistent. But the stories themselves were often described as, well, predictable, safe, and kind of formulaic.
Technically sound, but maybe a bit boring, sticking to the well-trodden path.
Pretty much. Following typical patterns but lacking real inventiveness.
Okay, and what about the star combo, MLA+RoPE?
In stark contrast, MLA+RoPE, especially at that RD2 sweet spot, consistently produced what they described as the most coherent and engaging narratives. The qualitative examples they showed were much better at tracking the narrative state, remembering details introduced earlier, and maintaining consistency over longer contexts. It rarely seemed to lose the thread.
Which lines up perfectly with its high consistency and creativity scores from GPT-4.
Exactly. And they noted these differences were most pronounced in longer story continuations. That suggests the benefits of MLA+RoPE, particularly RoPE's contribution to maintaining context, become increasingly critical when the model needs to keep track of more information over extended text.
It really sounds like that combination unlocks both efficiency and potentially better narrative flow, especially for longer outputs. That's impressive. However, like any good research paper, I assume they pointed out their limitations.
Oh, absolutely. And they're quite clear about them, which is good science. First, domain specificity. All their experiments were conducted on the Tiny Stories dataset, which is relatively simple English narratives. How MLA+RoPE behaves on more complex data. Think technical documents, computer code, or even multilingual text is still an open question.
Right. Proven on simple stories, but needs more testing for complex, real-world tasks. What else?
Training duration. The models were trained for only 50,000 steps. It's possible that longer training might alter the dynamics, perhaps allowing more compressed models to eventually catch up further in quality. Also, the compression itself. They only tested a few fixed values for the latent dimension R, like D, D2, D4. Exploring adaptive or more compression ratios, where maybe R could vary per layer or even based on the input sequence, could be a fruitful direction.
Makes sense. Any hardware limitations?
Yes, the performance benchmarks, the speedup numbers, were specific to NVIDIA A100 GPUs. The efficiency gains and speedup characteristics could definitely differ on other hardware platforms, like mobile phone chips or CPUs, which are precisely the kind of resource-constrained environments where you'd most want to deploy these efficient models.
So performance might vary on your actual phone chip and the evaluation.
The GPT-4 evaluation, while scalable and providing interesting insights, is still an automated metric. Comprehensive human evaluation across a diverse range of tasks and users would obviously provide a more definitive picture of the real-world perceived quality.
Got it. But as you often say, these limitations aren't just downsides. They really point the way towards exciting future research directions, don't they?
Precisely. The paper itself implicitly and explicitly points towards this. Things like testing MLA+RoPE on diverse domains and languages, developing more sophisticated adaptive compression techniques, combining MLA with other known efficiency methods like quantization or pruning, could they be synergistic? Conducting a deeper theoretical analysis to really nail down why RoPE has this surprisingly powerful, almost protective effect on compressed attention. And of course, the ultimate goal, real-world deployment studies on actual edge devices to see how these techniques perform in practice.
So bringing this all together then, what's the big takeaway from this deep dive into latent multi-head attention and rotary positional embeddings?
I think it's crystal clear that architectural innovation is absolutely paramount if we want to bring powerful language models out of the cloud, out of the data center, and onto the devices we use every day.
Yeah.
MLA offers a genuinely clever, mathematically grounded way to attack that major memory bottleneck, the KV cache.
And the really innovative finding, the core academic insight here.
For me, it's the discovery, or at least the strong evidence, that RoPE isn't just a useful add-on for positional information, but appears to be critical for enabling these compressed attention mechanisms like MLA to function effectively and maintain quality, especially in smaller models. It enables the compression without leading to that catastrophic failure we discussed. That synergy is key.
It really does challenge that default assumption in AI that you just need to scale models bigger and bigger to get better results. For the countless devices out there where memory and processing speed are strictly limited resources, clever design, clever architecture is essential.
And MLA plus RoPE is presented here as a significant step towards that goal. It demonstrates beautifully, I think, that by carefully co-designing how attention works and how positional information is encoded, you can achieve really impressive efficiency gains. We're talking reduced memory footprint, increased speed.
While crucially preserving model quality for the most part.
Exactly. It's a key piece of the puzzle for making genuinely capable AI accessible on the hardware that most of us interact with every single day.
This study really makes you think about the future of AI accessibility in a slightly different light, doesn't it? Could techniques like this MLA plus RoPE combo be what finally allows truly capable conversational AI to live comfortably on your phone, or power the sophisticated AI features in your car rather than constantly needing that connection back to a massive server somewhere? What really stands out to you from this whole exploration of compressed attention and positional embeddings?
For me, it just underscores how much value there still is in digging deep into the fundamental components of these neural networks, understanding how attention works, how position is represented, how these things interact, especially when you start pushing the boundaries, like trying to achieve extreme efficiency. Sometimes the devil and the really exciting innovation is hidden right there in those details.
A great point to end on. Thanks for joining us for this deep dive into the latest in efficient language models.